Hello, my name's Eric, and I'm out here on the Bonneville Salt Flats because I want to talk about an experiment I'd like to do out here. And that is an experiment to test whether or not we live in a subjective universe or objective universe. You see, Albert Einstein framed the universe in his theories of relativity to being 3 dimensions of space and 1 dimension of time. And ever since then, we haven't been able to understand quantum mechanics because I believe that's the wrong way of looking at the universe. I believe we live in a 4-dimensional objective reality. And this experiment would show that. Now you might wonder, how is this experiment going to show that, and what is the experiment? Good question. On the salt flats here, I would have 4 quantum clocks. Quantum clocks are the most accurate clocks in the world. I don't even know where I would get them. But if I get enough people spreading this idea out to the world, maybe you guys can help find out where I can pick up a few of these. I haven't been able to find them on Amazon anywhere. And I would need 2 autonomous driving vehicles. Vehicles that can drive themselves at high velocities accurately here on the salt flats. And the way this experiment would work is that the quantum clocks, you'd have 1 each on each vehicle and 2 of them in the center. I guess I could get away with 1 in the center, but I'd need to have at least 4 displays to display the time from that quantum clock to the other observers. Because what I'm going to do is we're going to start these quantum clocks in the center of the plateau here, and they're all going to be synchronized with one another. And then the autonomous driving vehicles will start driving in opposite directions, computer perfect patterns at the same velocity, at the same time, just in opposite directions. And on even passes, when they both cover the same distance north to south at the same velocities, when they observe their time dilation relative to the other clocks, both the 2 that are stationary and the other observer that's moving in motion relative to in the opposite direction, then that's where the real rubber meets the road, or the salt, in which, in Albert Einstein's theory, he suggests that it's subjective, that each observer, both of the ones in motion and the ones stationary, all get to determine they're stationary and the other observers are in motion, because he believes that the universe is subjective. It's all about your position from which you get to determine who's in motion and who's not. And I say that's not the case. We live in an objective reality, a 4-dimensional one. And that means that each observer is going to observe time dilation in congruence with the idea that they're either on the vehicle or they're stationary, and their time dilation they observe is going to reflect that. So the ones that are stationary are going to observe they're stationary, and the vehicles in motion are experiencing time dilation. And each of the vehicles in motion are going to observe on their clocks a time dilation that is more or less equal to one another. Since they're both in motion, in the same velocity, in the same direction, they should observe the same time dilation relative to the stationary clocks. And this violates Einstein's understanding of the universe. And if I can show that we live in a 4-dimensional objective reality, I can answer to you how quantum mechanics actually works. It works because if you think about Einstein's bubble paradox, he had a problem with the idea of quantum mechanics in that he thought that the universe was 3-dimensional. See, his bubble paradox states that he imagined a photon as a bubble of light moving away from the source at the center at the speed of causality, or the speed of light as we know it. Then that bubble eventually will collapse, as quantum mechanics predicts, at some one point in that entire surface of that sphere, that bubble. And the information of the collapse has to happen instantaneous to the entire bubble to ensure that it all collapses at one point and not any other point. And he believed this broke the laws of physics because the information has to travel faster than the speed of light. He called it spooky action at a distance. He then later restated it using 2 photons and the events collapsing simultaneously and communicating with the other photon instantaneously. Now, he would be right if we did live in a three-dimensional universe, but if we live in a four-dimensional universe, where the fourth dimension is like the other dimensions, at least from the perspective of the photon, that means what's really happening is that we're the ones in motion and the photons are stationary. Especially thinking of those two photons. They're stationary in the fourth dimension. Being point particles, they exist in only one dimension at a time. So they're stationary in that dimension, and they're not moving relative to each other. They're stationary right next to one another. Even though from our perspective, they look like they're on opposite sides of the lake or the universe, which in reality they're not. That's just our perception and our interaction with their potential position when they move from the fourth dimension to one of the other three physical dimensions we observe. That's what we think of as a collapse, when it moves from the fourth dimension to one of the other three physical dimensions. Now, the reason why it takes on this wave-like motion instead of its normal particle motion is about our velocity through the fourth dimension, because we're in motion through the fourth dimension at the speed of causality, and the photon's stationary. So our perspective on anything that's stationary in the fourth dimension is going to take on a distorted perspective. We're going to observe it as though it's spherical. And the photon moves from the fourth dimension to one of the other dimensions, instantaneously collapsing. From our perspective, it's actually just moving from one dimension to another. From our distorted dimension, from distorted fourth dimension, from our perspective, to one of the three physical dimensions, undistorted. Now, the reason why the photon's stationary is the same reason why a soccer ball shot out of the back of a pickup truck via an air cannon, which, if you guys are fans of Mythbusters like I am, you'll have seen this episode in which they drove an air cannon on the back of a truck, put a soccer ball in it, shot it out at 40 miles an hour while they were driving at 40 miles an hour in the opposite direction, and that soccer ball remained stationary relative to the road. Well, if you replace the road with the fourth dimension, and you replace the truck and cannon with us, and we eject the photon, which is the soccer ball, out at the speed of causality when we're moving the opposite direction at the speed of causality, that means that the photon will be stationary relative to the fourth dimension. We're the ones in motion, the photon's not. And another reason why we have to live in a four-dimensional universe would have to be the path the electron takes around the atom's nucleus. It cannot be measured or tracked in 3 dimensions because it's doing it in 4 dimensions. And because the fourth dimension, from our perspective, takes on the appearance of time, or maybe it is time, its relative motion to the fourth dimension takes on what we think of as time. Therefore, it can happen in ways that we think couldn't happen in our universe because it doesn't obey the same rules. It's moving through the fourth dimension, all 4 dimensions, in its path around the nucleus. So it will seemingly go faster than the speed of light from our perspective. That being said, I don't know, I haven't thought of an experiment to test that idea. That would be the 3rd experiment. And I'm hoping you guys can help me out, because I ain't got the pocket change to put together this experiment here on the Salt Flats. I don't have electronically controlled vehicles that can carry quantum clocks and displays and high-speed cameras and all that sort of thing to make the observations with. I need help getting this equipment together so we can test this. And I hope that you are excited about the possibility of these new physics that we're going to be discovering. Because if we can do this together, I believe it is possible to create technology to allow us to create an inertial dampening system for a spaceship, which means we can accelerate up to the speed of light faster and decelerate from the speed of light faster, if I'm right. Now, that is very complicated and, well, financially, I don't want to just give it away. I want it to be invested into the proper ideas. So, and here's a thought experiment I like to spring on people. Let's imagine you were going to travel to a star system that was 10 light years away. And you had two ships that you could get on. The first ship was warp technology. You got in that spaceship, it creates a space warp bubble around the ship, and then moves the bubble through space at twice the speed of light. So you're going to go warp 2 is what they would call it. And you'll get to that star system that's 10 light years away in only 5 years. And then there's your second spaceship. That's my spaceship. We have the inertial dampening system, and we can accelerate up to almost 99.9% the speed of light in only 1 year, and then decelerate in 1 year. Now this is new technology and may be able to improve that, but 1 year is what we got. So the idea is we're going to that star system over there, but it'll take over 10 years to get there, because it takes a year to get up to speed and then a year to come down from that speed. But for the time between then and there, that distance is covered at the speed of light. So 10 years plus. And the question is, which one would you want to get on? Now, you can think, 5 years, that's half the time, or less than half the time. I'm going to go on that one. Well, good luck to you, because your experience is going to be, you experience 5 years of space travel, stuck in that spaceship all the way there. My experience will be roughly 2 years of time travel to get to that, even though from everyone else's perspective, it'll look like I am moving at light speed or even less than that, which means it'll take 10 years to get there from everyone else's perspective. Because my time is being dilated, I will be put into suspended animation for the time that I am moving at the speed of light. So only the time I'll experience is getting up to light speed and coming down from light speed. And in fact, the beauty of that system is that if I'm traveling to some place that's 100 light years away, it'll still only feel like 2 years. We will need a minimum of 2 years of life support, food and water and all that, to get there. Now, obviously, if it's Colony Planet, you'll want more than that for your time and effort it'll take to set up a colony, or go to a different star system. So you'd want to have more, but it would be no different equation if you're going in the warp speed technology. Although with the warp speed technology, let's just say I took 5 years of food in my spaceship, and it took 2 years from my perspective to get somewhere, and it turned out not to be a good place. We calculated it wrong, but we got another one that's another distance away, another 20 light years over there. We can go to that one and check it out. Another 2 years of resources used up for that. But if you're in the warp one and you go to that space, that colony space, you get there and the planet's not good, there's something wrong with it, you've used up 5 years of your resources to get there. And that 20 years one, that'll be 10 years. So to make it there, you need an additional 10 years of food and life support. And unless you're replenishing that on the way, you're going to be in trouble. Whereas I can get there without an issue. That being said, I hope you guys can spread the word, and maybe some of you guys can even understand my theory as it stands and why I need to do the experiments. Maybe you guys can reach out to someone like Elon Musk. I think he can help me get my hands on the automatic driving vehicles. I don't know how big quantum clocks really are, but if those semis are anywhere capable of hauling them, we might be able to do that experiment out here. It's hard to say. I don't know. But I hope you guys can help. That's enough for this video. I'm sure I'll give you another lecture on another time, at another place. See you later.